Welcome to STEM Talk.
STEM Talk.
STEM Talk.
STEM Talk.
STEM Talk. STEM Talk.
Welcome to STEM Talk, where we introduce you to fascinating people who passionately inhabit the scientific and technical frontiers of our society.
Hello, I'm your host, Ken Ford, chairman of the Double Secret Selection Committee that selects all of the guests who appear on STEM Talk. Today, we have Dr. Pascal Lee, a planetary scientist at the SETI Institute, a not-for-profit NASA program focused on searching for extraterrestrial intelligence in an effort to understand and explain the origin and nature of life in the universe. Pascal is making his third appearance on STEM Talk. Much of his research focuses on asteroids, impact craters, and future human exploration of Mars. Our interview with Pascal today comes at a time when there's growing momentum for space exploration and manned missions to the Moon and eventually to Mars. Pascal is a co-founder and chairman of the Mars Institute and director of the Haughton-Mars Project at NASA Ames Research Center. Last year, Pascal received significant news coverage for his discovery of a giant volcano, along with a possible sheet of buried glacier ice in the eastern part of Mars' Tharsis volcanic province. This was the first geological find of this magnitude since the other major volcanoes on Mars were discovered back in the 1970s. We will talk to Pascal about his discovery, but before we get to our interview, I have some housekeeping to take care of. First, all of us at STEM Talk really appreciate all of you who have subscribed to STEM Talk, and we are especially appreciative of all your wonderful 5-star reviews. As always, the Double Secret Selection Committee has been continuously and carefully reviewing Apple, Spotify, and other podcast suppliers for the wittiest and most lavishly praise-filled reviews to read on STEM Talk. If you hear your review read on STEM Talk, just contact us at stemtalk@ihmc.us to claim your official STEM Talk t-shirt. Today, our winning review comes from a listener going by the moniker Adventurous Lie 975. The review is titled, "Anyone Catch the STEM Talk Episode with Vivian Lowe on Arthrosclerotic Disease?" The review reads, "Love the STEM Talk podcast. I highly recommend it as the topics are varied and well-researched. This episode was so interesting, and I wanted to share here in case anyone missed the episode." Thank you, Adventurous Lie 975, and thank you to all our other STEM Talk listeners who have helped STEM Talk become such a great success. Okay, and now on to today's interview with Dr. Pascal Lee.
STEM Talk. STEM Talk.
STEM Talk. STEM Talk.
Pascal, welcome back to STEM Talk. You, my friend, are now part of an elite handful of folks who have been on STEM Talk 3 times. Your last guest appearance on STEM Talk was in 2021, so welcome back.
Thank you, Ken.
Since then, a lot has happened in terms of space exploration and our ambitions to send humans back to the Moon and eventually to Mars. We've had the first mission into space with an all-civilian crew. NASA has made big strides in its Artemis campaign, which is scheduled to return humans to the Moon next year for the first time since 1972. But I'm not holding my breath. And the big goal, the overarching goal of sending humans to Mars, actually made it into President Trump's inauguration speech. For someone who invested so much of his life and career in the advancement of space exploration, this must be an exciting time for you.
Yes, it is. It is. You know, the return to the Moon is one of those things that we would have expected to have happen much sooner. And even the journey to Mars, I had always hoped that we'd be much farther along by now. But you're right. This is feeling like it's going to happen soon. Although, of course, you know, at this very minute, there's still a lot of uncertainty as to the extent to which we will commit to establishing a permanent presence on the Moon, which I think is really what we need to be doing. And then, of course, how we will go to Mars, where we might land, who will go, how soon, etc. So, but it is an exciting time, and it hasn't been this exciting for a long time.
For a couple of decades now, you've been visiting Devon Island in the Canadian Arctic archipelago. When we talked to you back in 2021, you unfortunately had to cancel your annual summer trip due to COVID. Devon Island, as some of our listeners will remember from previous interviews, is the Earth's largest uninhabited land with a geological characteristic similar to what we kind of anticipate on Mars. Since 2001, Devon Island has been the summer home of the Haughton-Mars Project. You were eventually able to return to Devon Island in time to celebrate the 25th anniversary of that really interesting project. Can you give us an update on where the whole project stands and how things are going now in terms of that project?
Yes. I mean, we've been at this Devon Island thing for the past 25 years. Looking back, aside from the two COVID summers, I've spent every summer of my life on Devon Island in the past quarter century. And that's mainly because the place has so much to offer. The geology, we're still getting to the bottom of it. We're studying canyons, which look so much like some of the canyons on Mars. On Devon, they are of glacial origin. We think that the ones that are equivalent on Mars are also of glacial origin. It's not always the case. I mean, sometimes, things that we see on Devon might not actually have a direct counterpart on Mars. But in the case of these canyons, it really looks like it is the case. The impact crater itself, which is one of the main attractions while we go to Devon. Our project is called the Haughton-Mars Project. It's named after the Haughton meteorite impact crater on Devon Island. And Haughton crater is 23 million years old. 20 kilometers in diameter. It's a large impact structure. And we are, for example, realizing that one of the products of the hydrothermal activity that was triggered by the impact were sulfate deposits. And sulfate deposits are actually one of the most intriguing recent finds at the surface of Mars. And not only that, but it is suspected that sulfate deposits imply environments that had lukewarm waters circulating, hydrothermal activity, places that are very conducive to the possibility of life on Mars. And so our study of these polyhydrated sulfates that we're finding on Devon Island is feeding directly into interpreting the implications of the recent discovery of polyhydrated sulfates on Mars as well. And then the other thing is polyhydrated sulfates are called that way, polyhydrated, because they contain a lot of water. And so when you bake one of these giant crystals, they come in the form of these translucent slabs. When you bake one of these giant crystals of polyhydrated sulfate, you can extract something like 50 to 60% by mass of water out of them. And so polyhydrated sulfates on Mars, therefore, could be a significant repository or source of water for astronauts to access, in the sense that they're very stable. You just chip away at them, you carry them home, and then you bake them. You bake the water out of them. If you have plenty of power on Mars, then it would be not an unreasonable way of extracting water.
Although we've been discussing Mars, and certainly a human mission to Mars would be fascinating, I think in both our minds, a mission where we return humans to the moon and build a fixed lunar base there with a fleet of mobility vehicles, this kind of mission is certainly a more immediate and important goal in the near term. Can you touch on the importance and significance of returning humans to the moon?
Yeah. Obviously at this point, the moon is a very important destination in and of itself. Even if we were not going to Mars, it would be, I think, imperative for several reasons for us to return to the moon. The usual one, the geopolitical one, sort of the strategic importance for any nation that's spacefaring to sort of be where the competition is active is an important thing. Just like in Antarctica, where many nations are present, not because of science, but because it's important to be there geopolitically. And then, of course, once you commit to being there, science is what you do. So science dominates the activity while you're present in Antarctica, but it's not the motivation for nations being there. It's sort of the same thing with the moon. We're going to do a lot of good science on the moon, but we're not going there for the science. We're committing these large resources, China, the United States, other countries that are planning to go to the moon, are committing large resources because it is strategically important for them to be present on the moon. So I think for that reason alone, we have to be going back. I, of course, am seeing the moon as a scientific jewel. There are so many things that we can explore. To me, one of the most intriguing recent discoveries on the moon, well, it's over a decade by now, is the discovery of caves, pits and caves on the moon. And, on Earth, caves are usually, at best, just geological curiosities. Even though we understand that the underground realm is is sort of a different environment from what's prevailing at the surface. We don't expect there to be, there isn't this huge contrast in environmental conditions between the surface and the inside of the cave as what you see in the case of the caves on the moon or even Mars. On Mars and on the moon, the surface is lethal for any form of life from Earth, even extremophiles, whereas caves are all of a sudden sheltered environments. When you're in a cave on the moon or Mars, you are protected from the ionizing radiation from space, both from deep space and solar particle events. You are subject to dampened temperature variations. You are protected from micrometeorite impacts. All of a sudden, caves are the difference between something that is much more survivable for life on Earth versus the surface. And so, of course, humans could not just be dwelling in shirt sleeves in a cave either on the moon or Mars, but there are life forms that on Mars could, for example, eke a living if they were in a cave, with some source of water vapor and warmth. And that is, to me, a very intriguing possibility. The real drive, in my sense, to explore caves on the moon is the prospect of having to do that on Mars. We want to be able to explore caves on Mars because that will open the door to accessing the underground realm of Mars, in which extant life that's still alive, might be present. We now generally believe that the surface of Mars is too hostile for any form of life, but going into a cave would be an entirely different thing. Some terrestrial extremophiles could survive in caves on Mars, and therefore there might be Martian life that is somehow happy enough to thrive inside caves on Mars. We want to explore that form of life. We want to understand it. How alien is it from Earth life? And to practice, to get ready for that encounter, we should explore caves on the moon, in which we don't expect to find alien life, of course, but it will be a good practice for what we hope to find on Mars.
Continuing with the moon, currently the plan is to send humans to the South Pole region of the moon. And you've written a paper on that topic. The paper is titled An Off-Polar Site Option for the NASA Artemis Base Camp. So, what do you see as the primary weakness of the current plan, and what might be the advantages of not going to the South Pole region? This is what always comes up. It always comes up, South Pole, access to water, issues like that.
Yes. So as much as I am totally on board the United States returning to the moon in a sort of fast and aggressive and high pace, I'm concerned about the focus right now that we have on the South Polar regions of the moon, or even if it were the North Pole. The polar regions are attracting us there because there's the promise of being able to extract water from the near-surface regolith, the soil of the moon. Now, let's look at the numbers. One of the highest concentration areas that we've been able to explore with the L-cross impact, so it's a on-purpose impact of a spacecraft into the lunar soil near the poles. A plume of dust and gas was developed from the impact, and that gas was analyzed, and it was confirmed that there is indeed water in the ground at the South Pole of the moon, but the concentration of this water is 0.5 weight percent, meaning that if you extract 1 metric ton of soil on the moon, you will get 5 kilograms or 5 liters of water at best. Now, that is a very small amount. That is less than the water that you would be able to extract from Sahara sand on Earth. It's of that order. The point here is that there isn't that much water in significant concentration, at least at regional scales at the South Pole of the moon. There might be places where you actually have clumping and ice lenses in the ground, which of course we want to discover, but we don't know if they exist. And in any case, even if there were concentrations of water at the South Pole of the moon, it would be a huge and difficult task to extract it. Nobody's saying it's impossible, but one has to realize that there would be a huge cost to doing that. First of all, much of the water is in ground or in areas of the surface of the moon that are permanently shadowed, and therefore temperatures that are of order 50 Kelvin. I mean, the temperature at the surface of Pluto is around 40 Kelvin. Okay, so you're talking about extremely low temperatures in which we have zero experience operating moving parts, robots with moving parts, machinery. I mean, even though the Voyager spacecraft and New Horizons spacecraft has flew by Pluto, they don't really have, at that point, lots of moving parts on board operating at temperatures of 50 Kelvin. And yet that is what we would be dealing with in the south polar regions of the moon. So, just because you have a bit of water in the ground of the moon, how would you extract that? If you expose it by stirring it, it will sublimate. If you have to not just extract it, but you have to contain it. Once you contain it, you have to separate it from the dirt and get really what you want, which is the H2O. We want the H2O, of course, because you can use the water for hydration. But more importantly, the idea is to break down the H2O into hydrogen and oxygen to make rocket fuel. Well, so then you have to pipe it. You have to pipe the water that you've extracted to a place that's warmer, where you might be refueling things. That in itself, I mean, people who have done plumbing in Alaska or in the polar regions know how difficult it is to keep your piping warm and the water flowing in there liquid. It's going to be extremely difficult to do that. And again, it's not a matter of shying away from a challenge or difficulty. The question really is, ultimately, will it really be more economically affordable to extract water from the moon with that great complexity and cost versus the alternative, which is to bringing it from the Earth? We are pushing with the maturation of the Starship system. And once Starship is mature, in one single landing on the moon, it can deliver 125 metric tons of water if we wanted it to. So all of a sudden, you have one Starship bringing in just water. With 125 metric tons of water sitting at the surface of the moon in essentially a water tower with a tap at the bottom, I sometimes joke, you have a clean supply of water that is coming from the Earth at some cost for sure. It will not be something that you really break down to make fuel, although you could. But you could recycle it, of course, and use it for hydration and the operation of a base. So that's sort of the competing scenarios where essentially we fly in the water that we need on the moon. And of course, it doesn't sound as elegant as this idea of living off the land, but you have to really analyze the concentration or the low concentration of water on the moon as possibly being not really a resource, but a scientific curiosity. Economically viable is something that is really difficult to achieve once you factor in all the costs of not just extracting something or exposing it, but getting it to where you want it, storing it, and using it. That's a whole chain of activities that's going to be very costly. And at this point, all I'm saying is that what we should be doing is double, triple, quintuple our robotic exploration efforts in the South Polar region of the moon. Go to all these places where we think there might be higher concentrations locally than elsewhere, and really get a thorough scientific understanding of the distribution of water in 3 dimensions here at the South Polar region of the moon. Meanwhile, these regions are very difficult to explore from the standpoint of their topography. The terrain is very rough. We're talking about lunar highlands in the South Polar region of the moon. The lighting from the sun is extremely challenging. The sun is at or below the horizon all the time, so you are constantly trying to escape getting trapped in a shadow. It's not the type of place that is conducive to long-range exploration from. So if you land somewhere, you're going to be maybe trying to time your mission with a bit of daylight. But then if you miss that, or if you're on some sort of a long traverse, you could get caught and trapped in a big patch of shadow, and all of a sudden your temperatures are plummeting. You're in a very risky environment for humans to explore at this point, without us knowing yet whether or not it's going to be really worth that risk, since we don't really have a full assessment or understanding of this water thing. So I would recommend that we, of course, return to the moon, but that the human side of the effort be focused on establishing a base. A base is the ABC of long-term presence, long-range exploration. It's what is a proven solution for exploration. We do that in Antarctica. You set up a base in a place that's relatively benign, easy to get to, logistically easy to resupply. We do that in the Arctic. Even with our little project, the Haughton-Mars Project, we have a base camp. And from there, with a mobility system, you radiate, you fan out to explore other places. And of course, the more capability you have over time at your base, the longer range and longer duration your excursions. So to me, in fact, the movie 2001 had it right. It had a big base on the moon in some place that was very open and not necessarily very attractive. But then the astronauts would take this little moon bus, it was called, a hopper that would fly across the lunar surface and get to this place where they unearth that slab. Of course, in this analogy, I'm equating the slab to a good place to extract water. So once we find that, yes, you can establish a mining operation at the South Pole in a location that, is really promising, and somehow you've worked out the numbers that you can actually extract the water economically. At that point, you have humans go there in a big way. And by then, of course, we would have a lot of lunar exploration experience. But for now, our focus really should be to establish a permanent foothold in a more benign off-polar site on the moon. That's what I would do from the standpoint of a sort of a good exploration strategy.
I actually agree with you on that. And, we tend, and when we think about human spaceflight and planetary exploration, there's a great tendency in the world, including NASA, to sort of fall in love with various romantic ideas.
Yes.
Like, quote, living off the land.
Yes.
When lunar operations will be so difficult, we don't need to make it exponentially harder.
Right.
It's right at the limit of what I think we could possibly do without making it harder.
Yes, exactly.
So it's there's this, maybe informed by television and science fiction and sort of just our natural human tendency to like sort of neat ideas. And it is a neat idea.
Exactly. I completely agree with where it's coming from. It's exactly that.
Right.
Yep.
Right.
Yep.
And we see it all the time in human
But
spaceflight.
it's not a pragmatic approach, and especially if you put in the actual uncertainties as to whether or not we actually have a resource here to behold.
Right.
Yeah.
Right. I can think of several other examples from past plans for what we might do in space with humans, and I'm sure you can too, that have the same flavor.
Yep.
Like, let's make it 10 times harder, but we probably can't do the easy version.
Yep.
Right. The easy version here will not be easy.
No, yeah. And, just to wrap up this analogy with, this alternative of a starship bringing 125 metric tons of water, that water would be recyclable. So when will we have 125 metric tons of clean, purified water extracted from the moon sitting where we want it? Even if it were possible, even if it down the road were economically viable, it would take decades and decades before that we even got to that point. So I really think that in terms of a good strategy for the short term, we should completely forget about these sortie missions to the South Pole. We might do the first one because we're so far along at this point, but refocus on setting up a base.
Following along in that theme, in your paper, you proposed a base on the floor of the Clavius crater. Can you just quickly describe this crater and why it's a better option, and why in particular the Clavius crater?
Yeah, so I actually looked at a number of options, I and students who are working with me on this overall survey, a number of options around the South Polar region. First of all, you want a location that is on the lunar near side. You might as well see the Earth, have direct to Earth comms from your location. It's a safety factor. It's also a psychological benefit, and it's just a good idea. So we have essentially half of the moon excluded from that up front. The second thing is you want a place that's wide open, that's easy to approach, launch from, land on. You want wide open areas that give you plenty of options to expand your base. And most importantly, you want a viable route, not just to go left and right into different places, but in particular towards the South Polar regions. Because there is still this interest, of course, in potentially extracting water from there. And there might be a phase during which we would explore the South Polar region with sortie missions from the base to the South Pole by pressurized rover. And we want it to be in a location where we'd be just a few days away from the South Pole. So that actually narrows things down pretty quickly, because the way the South Pole is set up, it's actually, there are barriers by giant craters and shadowed regions, permanently shadowed regions, that are really cutting it off, if you will, from the rest of the lunar near side. Clavius is 260 kilometers in diameter. It's the second largest impact crater on the near side of the moon, behind a crater called Bailly. And Clavius is very ancient. It's Nectarian in age, so it's around 3.8, 3.9 billion years old. And in the meantime, it has had a very interesting geologic history. We're publishing this shortly. In fact, next month, this is work that I've done with a student of mine called Aaron Sampson. So Aaron and I have found volcanic eruptions and ancient volcanoes on the floor of Clavius, we think. There are places where Jack Schmitt has pointed out that there are permanently shadowed regions even on the floor of Clavius. So it's not that low in latitude. It's still pretty high in latitude. It's around 60 degrees south. There is a big bright streak of ejecta from Tycho crater. Tycho crater is a very important recent crater on the moon. Jack Schmitt on Apollo 17 tried to sample some of that material that was ejected all the way from Tycho to his landing site. Sure enough, they found some material that was dated to about 108 million years, which is, of course, very recent, relatively speaking. So there's Tycho material also cutting across Clavius. But most importantly, there is a much more recent impact crater called Rutherford straddling Clavius, in which there are caves. And so then the caves of Rutherford, like the caves at higher latitudes on the moon, which I've been focusing on finding and studying in recent years, hold a promise of being cold enough to possibly have water ice trapped in them. And so being at Clavius gives us a nice opportunity, without having to drive too far away, to explore and learn how to explore a large number of caves on the moon, which of course in turn will pave the way for us doing the same on Mars. And then finally, the SOFIA mission, which was it's a stratospheric observatory for infrared astronomy. It's this airborne modified 747 aircraft that NASA used to operate in the stratosphere of the Earth to study the infrared universe. The SOFIA aircraft actually discovered a concentration of molecular water. So we're not even talking about detecting hydrogen here. We're talking about actually detecting H2O, the molecule of water, at the surface of the moon in the region of Clavius. And so we don't understand where this water is coming from. There are speculations that it could be from the impact that produced the recent Rutherford crater. It could be an impact from a water-rich asteroid or even a comet. This is something that Peter Schultz proposed. The bottom line is Clavius, all of a sudden, is turning into this real gem of a place that could certainly feed our scientific curiosity and exploration thirst while we figure out where we should be doing the digging and the excavating on the moon at the poles. And at the same time, it would really get us going down the road of exploring the moon and being there permanently. And of course, Clavius is where the movie and the book 2001: A Space Odyssey had its base. And that to me is, on the one hand, a trivial sort of sideline, but at the same time, there's something to this. It's another example of fiction turning into reality if we had a base there. We don't necessarily have to have this giant base that's portrayed in the movie. I mean, even 1 or 2 modules would constitute a base. I mean, an embryo of one. But the fact that we could establish a base at Clavius and be on our way to fulfill the vision of 2001, I think would be something very attractive to the public. So for now, we're still continuing our survey. We're looking at other places. But so far, Clavius has become the place to beat. And that's why we're sort of advocating Clavius for now.
Mm. How confident are you and the community in general with respect to the SOFIA finding of water in that location?
I'm not an expert in near-infrared spectroscopy, but the detection was made by Honeyball, who was a grad student at the time and wrote the paper with her advisor and collaborators. And the thing that's interesting is that it was a detection made during the certification, the pre-testing, if you will, of the instrument and the capability at the time. It wasn't an official observing run. It was more like a test. Right. But I have no reason to question the validity of that data. I mean, unless you've heard something different.
No, I heard just what you said, that it was in the calibration stage or the testing stage, as it were, early days.
Yeah.
I remember struggling to keep SOFIA operating and funded when I was at NASA. And I think it's met its demise.
Unfortunately, yeah. It's one of those things that was just an incredible capability, but
one hears the current interest in human exploration of space. And of course, all exploration of space is human unless one knows of another exploring species. So I actually don't like that phrase because they sort of contrapose it to robotic exploration. Yeah. But the robots aren't going there on their own accord or deciding, let's explore. It's all human exploration. But when we talk about sending humans someplace, lately it's kind of tied into geopolitical issues, just as it was with the Soviet Union and in the first trip to the moon. And now we see it sort of tangled with relations with China. And I wondered if you would talk about that and how you see that and how you think the United States should conceive of that.
Yeah, historically, nations support exploration only to the extent that exploration serves the national interest. I mean, unless you happen to be a king who's just curious about botany and wants to have samples from some weird place. President Jefferson sent Lewis and Clark out west at great cost. It was the Apollo program of the time, considering the cost of that expedition, the Lewis and Clark expedition. He sent Lewis and Clark out west not because he was interested in botany or wildlife, which he was, but the reason to send them out there was to understand who lived out there, what would be navigable routes, who could we trade with. And I say we, I mean the early colonies. So from that standpoint, the exploration was driven by national interest. Okay, and this has been true historically, I think, throughout human history. James Cook was not sent to the South Pacific by the British Navy because they were interested in botany. It was because the French were roaming those waters and there were lands and people to befriend and somehow conquer. So it's very clear that the motivation for exploration is usually, first of all, to serve national interest because of the resources that it requires. The second thing is that historically, it's the military who really led exploration. And it's subsequently that, civilian populations come in where you might commercialize your colonization efforts, like with the Hudson Bay Company in Canada. But to me, there's nothing unusual in the fact that we are competing with China, for example, right now to return to the moon. It's just something that we should expect. The thing, though, is that I don't think we United States should be caught up in a race that we've already won. The United States won that race to get to the moon in the 1960s. And so what is at stake for us now is not to beat China to returning to the moon. China might well put their astronauts on the moon in the next 2 years ahead of the United States' return to the moon. That to me doesn't worry me at all. What does worry me, though, is that we are cornering ourselves with this sortie mission approach. In other words, you land here once and then you don't really leave an infrastructure behind, and then you land some other spot next time, which is what we're planning right now with Artemis 3, Artemis 4, Artemis 5. We're landing in different locations on the moon each time, not really building an infrastructure. And to me, this is a really big mistake. It's something that we should convert into a winning strategy, which is to actually pick a site, not at the South Pole, but off-polar site, and set up shop there. And again, nobody's talking about a ISS on the ground at this stage. You don't need something that big. Even 1 or 2 modules that you could return to, where you might park vehicles, where you might build up a fleet of mobility systems over time, would be good. The other thing is we have to go nuclear for this. First of all, if we're thinking about Mars forward, you cannot run a base on Mars or even a human mission of any significance with solar power. I mean, even with Perseverance and Curiosity, we've already given up on solar panels where we're using RTGs to power them. So imagine a base on Mars. We have to go with a nuclear reactor of sorts, like we had in Antarctica in the early 60s and late 50s with the United States Antarctic program. On the moon, we have this issue, especially if you are off the poles, of having to survive the lunar night. So on the moon, you have 14 days of continuous sunlight, and then where things get hot, where you could have solar power, but then you have 14 days of night where you cannot use solar power anymore. And so how do you survive the lunar night? Nuclear is the solution. It's the way to go. Now, there has been for a long time talk of space-based solar power, where you have, giant solar panels capturing power in lunar orbit, for example, in this case, and then microwaving or beaming down the power to a base on the moon. I think that at that scale, the efficiency and sort of actual maintenance costs of all that has to really be further studied to be believable. But on a small scale, there are small companies now that are trying to offer space-based solar power sort of for localized science stations, for example, like a small weather station, or, in the case of the moon, some monitoring station. Or if you have a small set of payload, you could conceivably power it with space-based solar power, and that could actually be interesting, especially if you wanted to survive the lunar night with your payload. So small-scale powering, maybe space-based solar power. Large-scale, like a base, you got to go nuclear, and again, that's the only way that makes sense on Mars anyway.
It's the obvious solution, but again, we often don't pick the obvious. We'll pick something that makes it much harder. Were you involved in the Blue Sky study on power beaming to the lunar surface?
No. And I'm not surprised because that's definitely not my specialty.
So I rounded up the right suspects, I think.
Okay.
And there were some real passionate advocates, as you can imagine.
Yeah.
But in the end of the day, even the advocates saw it as impractical, particularly at scale.
Yeah.
We were talking about perhaps using it as a way of providing power to the small pressurized rover.
Yes.
And worked on that for a few studies. And it was super interesting, but not really a practical thing you would do if you were committed to succeeding at the mission itself, as opposed to doing something cool on the side.
Yeah, I see. I'd like was a report produced or?
Yes.
Oh, really? Okay.
I'll dig it up for you. There's a database that has them all.
Okay, great. Awesome.
So, we've been talking about China and its plans. In fact, it has a plan for a lunar mission with lots of moving parts. And it's I'm not really up to speed on that. Do you know much about it other than what's in the media?
I don't know much about it other than what's in the media, but there are several things that are worth pointing out. First of all, they already have their lunar landing hardware built. It's apparently undergoing testing, but we've seen not just diagrams and sort of PowerPoint slides, but actual photographs of hardware in clean rooms that are the size of a lunar lander and of a command module equivalent. The other thing that's worth noting is that China's lunar lander is not designed like the Apollo lunar lander, in the sense that on the Apollo lunar lander, you had a descent stage, which ultimately stayed on the moon. And so that was discarded. And then an ascent stage sitting on top of it, in which the astronauts, of course, rode down to the moon in, but also rose back up into orbit from the moon's surface to lunar orbit in. And the entire lander that the Chinese apparently have designed is going all the way down and coming back all the way up. So they have designed apparently a fully reusable lunar lander that will have to be refueled. So in some sense, their approach is more similar to Blue Origin's Blue Moon approach, where you have a lander that actually gets refueled in lunar orbit, presumably. And that is sort of an interesting sign that they are, really committed to long-term operations on the moon. I mean, the other thing is we've heard floated that they might be going to Tycho, which is, if you look at the moon, the most glorious and brightest patch of crater with radiating rays. So symbolically, I'm sure it'd be, when we look at the moon, we unless you know where Apollo 11 landed, you sort of have to squint and look for it. Here, landing at Tycho, you can possibly miss it. So I think they're trying a sort of a media coup with that. But Tycho in itself is a very interesting, recent, large crater on the moon. It's 85 kilometers in diameter. I mean, it's huge. It's got a central peak that's magnificent. And I think that even though China's announcing that it's aiming to be on the moon before the end of the decade, so before 2030, I wouldn't be surprised if they actually showed up in 2028, even 2027 for that matter.
I can imagine that happening.
STEM-Talk is an educational service of the Florida Institute for Human and Machine Cognition, a not-for-profit research organization investigating a broad range of topics aimed at understanding and extending human cognition, locomotion, health span, resilience, and performance.
We've been talking about the moon a lot in the context of Mars as well, and as an important step toward Mars. And in recent days, this seems to wax and wane, but in recent days, one hears more and more about not just traveling to Mars, as if that is easy. And for our listeners, Mars is the moon cubed, at least in difficulty. I would say more than cubed. It will be very difficult. But people aren't just talking about traveling there or having what you might call a sortie mission. They're talking about colonizing Mars, which is an incredibly inhospitable place. And I wondered what you think is stimulating all of this interest. I often hear space exploration advocates say, oh, pish on the moon. We don't want to go to the moon. And that's because they don't want to go anywhere, right? If you tell me you don't want to go to the moon next, you're also telling me you want to shut down planetary exploration because the next step after the moon is tremendously more difficult.
Yeah.
So could you tell me where this is coming from, this colonized Mars? It's not just in the media, but you see people that ought to know better talking about it.
Yeah. Well, I think that a lot of it is rooted in the beauty and familiarity of the Martian landscape. It looks like Arizona,
Yeah, it does.
Utah. It looks like it's eminently colonizable, habitable. Why don't we just move in? Sure, it's cold. Let's just stay warm. Sure, there's no running water. Well, but there's ice. Let's thaw it.
Yeah.
So from that perspective, it's a very attractive place. Now, the problem, of course, is that if you're talking about operating a base there with a small population, but a permanent human presence, I can see that being something that could operate at a scale and cost that will be huge, but worthwhile because we're doing science, because we're exploring, etc. But Mars is not. I have this talk that I gave where I list the 5 things that will kill you on Mars in chronological order of cause of death. First of all, the atmosphere is super thin. If you're not protected in a spacesuit, you would essentially die within seconds from being exposed to the low pressure. Then you have the CO2. The CO2 of the Martian atmosphere is not breathable. It's actually poisonous for you, and you need oxygen to breathe. There's no free oxygen on Mars. So you're talking about, if you're thinking about having a population on Mars, you're talking about essentially creating a cocoon to allow that population to survive on a planet where there is no running water to flush away your waste, to dispose of things, where you have to recycle everything essentially to keep things warm and thawed. We have no place where we do this on Earth. We have no place where we do this on Earth. And once again, it's not about saying that it's technically impossible. The question is, at what cost and for what purpose? A life support system that a crew needs is essentially an intensive care unit. Why would you want to raise kids on Mars in an intensive care unit, in a place where they would never have a breath of fresh air, where they would not know the outdoors as we know the outdoors? I think some people who see Mars as this promised land are, for some of them, trying to escape the reality of the Earth. And that is not a good reason to go to Mars. You don't want to be going there for escapism. But the other thing is this notion of that you hear quite a bit, and Stephen Hawking mentioned it, Elon Musk mentions it, which is to create a multi-planet species because it's an insurance policy against something bad happening to humanity here on Earth. I mean, to me, this is profoundly flawed because you have to, imagine what it would take for Earth to be less habitable than Mars.
Exactly. I was just going to say that. Tell me what disaster would befall Earth to turn it into Mars.
No amount of nuclear war would make Earth less habitable than Mars. No amount of asteroid impact would make Earth less habitable than Mars. So, if you want to just save our DNA somewhere, well, you can stash it in some freezer bank on the moon, on the far side, and you'll be just fine that way.
Pascal, you missed several of the other, you only told us 2 of the ways Mars kills you.
The third way, so the CO2 issue, it kills you in minutes because you need oxygen to your brain and then you're brain dead. The third thing, of course, is the temperature. The temperature on Mars is on average minus 80 degrees Fahrenheit, that's minus 60 degrees C. You're frozen to the bone by sundown if you were exposed just under open air on Mars. If that didn't kill you, then the fourth thing would be the dust. The Martian dust is bad news for 3 reasons. It's very abrasive, so it's going to tear up the tissues of your lungs. It's toxic. It's replete with perchlorates, peroxides, which will attack your thyroid, and that's bad. And then the third thing is that it's extremely fine-grained, which means that it will clog the pores of your lungs. You will have what is known on Earth as Miner's disease or silicosis. You will lose your breathing capacity over time. So breathing and ingesting Martian dust basically kills you over the course of a few weeks. In the movie The Martian and the book, this notion of scooping tons of Martian dirt and bringing it into the cabin to grow your tomatoes or potatoes is a very bad idea because Mark Watney, the Matt Damon character, would be dead within a few weeks if he had actually done that. And then finally, it's space radiation. Space radiation will zap you even at the surface of Mars. We have this fixation about space radiation being a showstopper. It's actually one of the last things that will kill you on Mars. But of course, it's one of those things that is hardest to shield yourself against. To me, the solution is not to find a cave, which is, of course, another bag of worms of risk and uncertainty at this point, but to simply sandbag your surface modules, to the point where you are now properly shielded from space radiation for long-term stay. Sandbagging is a good idea rather than burying a whole module in just tons of dirt, because with sandbags, you can move them away, you can move your modules, you can reconfigure your base. You have this modularity that is preserved by having, some robot outside piling on sandbags to cover your module. So to me, sandbagging is the solution for the moon. It's also the solution for Mars.
You missed what I think of as the first way that Mars will kill you, EDL. Entry, descent, and landing.
Oh, yeah.
Mars is a nightmare for
yes,
EDL.
Absolutely.
As you said, very little atmosphere, so it's not going to slow you down much, but it's enough to burn you up.
Well, that's the thing, Ken. We also talk about how space radiation will kill you on your way to Mars and back, but I mean, you're going to launch on a giant rocket to start with. I mean,
Yeah, no risk there.
No risk there, exactly.
And then you'll be on a very long mission and be so deconditioned by the time you actually get to Mars. It'll be interesting to see how they do with respect to mobility and even donning the suit.
Yeah, and you need time. This is why I think short missions on Mars, because there are still scenarios that are considered for sortie missions to the surface of Mars, are really not a good idea. You once again, you don't establish an infrastructure for long-term exploration, so it's a very short-sighted approach. But the other thing is, you have to take into account this deconditioning that you just mentioned that is going to take its toll and will eat at the time that you have to explore on a short-stay mission.
For sure. And just even the psychological and human factors of a very small vessel traveling for a very long time. People imagine the astronauts will be looking out the window and look at those pretty planets. When they look out, if they look out, it'd be nothing but black.
Yep.
So last year, in his speech to his SpaceX employees, Elon Musk said that he expects 1 million people to be living on Mars in the next 20 years. That's a lot of people. That means if we had started when he said that, it would be 50,000 people a year. So what do you think about that, Pascal?
Yeah, I don't share that vision, dream, or even prediction. That's not an inherent criticism of the idea. I personally am motivated to send humans to Mars because of the exploration. To me, Mars is the closest place where we might have a chance to actually find the first example of an alien form of life. Of course, we're not talking about civilization. We're talking about microscopic forms of life, microbes. And that quest is really important because if we could find an example of an alien biology, all of a sudden that would expand our understanding of how life formed, what is common to different forms of life in the universe, possibly, and yet more specific. It would be a huge and profoundly impactful discovery to find an example of an alien form of life. Today, we don't think we can find that at the surface of Mars. I often say, even to, at workshops, that what we're doing with perseverance and curiosity, while it's very exciting and it's sort of an engineering feat every day, to me, scientifically, we're missing the point. Because even if you found a giant fossil on Mars with these rovers, let's say you're driving through this valley, there's a road cut, and you see giant bones sticking out of the wall. Okay, sure, you would publish that. You would say that you found signs of life on Mars, but you would not be able to establish for sure that it's alien life that you found. And that's because Earth and Mars are not isolated planets. They swap meteorites. Large impacts from asteroids and comets take place on Mars. They lob Mars rocks into space. They land on Earth. We have in our collection today over 300 meteorites that have come from Mars. Conversely, Earth rocks get thrown into space by large impacts on Earth by comets and asteroids. Earth rocks most probably are sitting on Mars. We know that they have reached the moon at the very least, and that's actually one of the most incredible discoveries from the Apollo 14 mission. But you could have Earth seed Mars with Earth life. Life could then have evolved on Mars, but ultimately that's not alien life, that's just exported Earth life. And if you found just a fossil, you would not be able to tell that it's really alien life. It could just be Earth life that evolved and became something big on Mars, but it's not the discovery of alien life. And in order to establish that what you found is truly alien, you have to do a few things that you can do. You have to look at the genetics of it. All life on Earth is genetically related. Alien life presumably would be genetically different and not fit in the Earth genetic tree of life. The other thing is you could do biochemistry. All proteins used in life forms on Earth use the same set of 22 amino acids, 20 to 22. It's actually quite incredible. Among thousands of possible amino acids in nature and available here on Earth, including brought in sometimes by meteorites, Earth life uses only the same set of 20 to 22 amino acids. And not only that, only the left-handed version of those amino acid molecules, not the right-handed ones. And the idea is that if you found a form of life on Mars and looked at its proteins, maybe it's using a different set of amino acids altogether, or maybe it's somehow using the same 20 to 22, but the right-handed version. In any case, you could also do that. That's not genetics anymore, it's just biochemistry. But there are ways to establish that a life form is alien. But in order to do that, you have to find it alive, or at least not dead for so long that its genetic material and biochemistry have been essentially erased. Therefore, to answer this question of whether or not we are alone in the universe, whether or not Mars has life, this question can only be answered by finding life that's still alive today. That's why we have to go explore Mars. That's why we have to go into caves. That's why I'm interested in exploration. So back to your point, I don't see the point of 1 million people living on Mars, living in an intensive care unit, which is what a life support system or dome is.
But it's also full-on delusional from an engineering point of view.
Completely.
I mean, it's just not. It's hard to imagine something less possible than that.
And, Starship is not really taking us in that direction. First of all, it's chemical propulsion. I think the real future for Mars exploration is to go with nuclear thermal propulsion. General Atomics has come up with a big announcement recently that, the types of fuel, they found a solution to the hydrogen fuel that would limit the amount of erosion that a nuclear reactor would undergo during propulsion to Mars on a mission like that. So all of a sudden, nuclear thermal propulsion is becoming, is one step closer to reality. So I don't know how Starship would accommodate nuclear thermal propulsion, but that to me is really the way to go, which then completely changes what you need to do ISRU-wise in terms of extracting resources on Mars to refuel your Starship. Anyway, that's one issue. But the other thing is, I think that a more likely future for humans is one day we will identify exoplanets that are not too far off in a relative sense, with actually habitable environments. For example, an oxygen-rich atmosphere. Well, right there, that would tell you that the planet is teeming with life. And the way to reach these places would be to either have multi-generational starships, which of course is difficult to achieve, hibernation, put human beings in stasis, that has some future possibly, but it's still a big question mark. The third possibility, of course, and you know this better than everybody else here, Ken, is androids with AI. Maybe those are our true offspring from a sort of a galactic exploration standpoint, where we might have one day essentially offspring that are synthetic and not subject to biological decay, death. And those might then be able to sort of colonize other worlds on our behalf.
And wouldn't even have to do it if it worked like the current large language models. They could just hallucinate that they were there.
They could just hallucinate that they were there. That's an interesting
We wouldn't
twist.
know the difference.
That's an interesting.
When they sent us the report, right? Later, I hope to talk to you about what I think is our shared favorite way to go to Mars without actually landing on the surface.
Okay.
But we'll talk about that. But before we do, I would like to talk about something really cool. Last year, you published a paper about a heretofore unrecognized Martian volcano. And this is really cool, finding a volcano these days. I thought they had all been accounted for like in the 70s or something like that. Maybe the 80s, I don't remember, but it was a while ago. So tell me how this happened.
Yeah,
and, that's pretty neat.
Growing up, I was interested in space in Mars, and I always thought, hey, gee, it would be great to one day discover something on Mars that, we didn't know already. But by the time I became a planetary scientist, the whole planet was mapped. All the, sexy giant features were found, recognized, and explained almost. We've known of volcanoes on Mars since the early 70s with the Mariner 9 mission, which clearly identified Olympus Mons and a few other volcanoes. So the way this happened was I had proposed, among many others, a possible landing site for humans at this incredible workshop that NASA organized in 2015, the one and only workshop to date that NASA convened to collect ideas of where humans might land on their first mission to Mars. And I had proposed a site that was in this region of Mars called Noctis Labyrinthus, the labyrinth of the night. I and my teammates thought it was strategically located. If you drive east from there, you enter the giant canyon of Valles Marineris with all its ancient rock layers, so you can look for signs of past life. And if you drive west from there, you climb onto the volcanoes and you can reach caves where you could look for signs of extant life, life that's still alive today. So the assumption already then was that the search for life, past or present, would be a huge driver of the scientific exploration of Mars, even though it's not the only thing going on, but it'd be a huge driver. We might as well be in a place that is really good for that, for long-term exploration. So we proposed a site that was in this nameless large pit, which we called Noctis Landing. And at the end of the workshop, one conclusion was, well, we forgot to specify that you have to also land near a known source of water. Okay, that NASA said that. So since that workshop, a lot of the focus on these landing sites has shifted towards the mid-latitude sites, the higher latitude sites, because our Noctis landing site was near the equator. The focus has shifted to the higher latitude sites because there we know there's ice in the ground near the surface on Mars almost everywhere. But it's not that it's easy to extract. I mean, even if it's right under your feet, people who've done work in the Arctic or Antarctica know that, permafrost is a real challenge. It's a harsh mistress. And so, to paraphrase the title of a book. And so, just because you have frozen ground underneath your feet, it's at minus 70 degrees C, it's very hard to extract, to even get to, let alone extract, etc. So nevertheless, it's there. And so following this workshop, a lot of focus moved to the higher latitude locations. So in the intervening time, with a student intern that I was working with, Surab Shubham, who eventually became a graduate student at the University of Maryland and is still finishing now his PhD there in geology. With Surab, we started to look for places where we might find signs of water near this location. And sure enough, at the outer perimeter of the exploration zone, several tens of kilometers from the initial proposed landing site, we found the remains of a glacier. We published that in 2023. This is quite a find in the sense that, well, it's a glacier to start with, but second, it's near the equator, where ice is not stable today. And the only reason why the glacier is still there, apparently, is because it is not actually exposing ice, but exposing salt. There's salt covering this glacier, and we think that beneath the salt, there still is ice. This salt deposit that we actually can see from orbit and map has all the features that you would expect from a ice glacier. It's got crevasse fields, moraine bands, thrust plains, foliation, all of these very characteristic geological features of ice glaciers. Except that we're not seeing ice, we're seeing salt. And not table salt, we're talking about sulfate. And meanwhile, this glacier is not completely exposed. It's actually blanketed in most places by a volcanic ash deposit. Technical term is pyroclastics. It's not just ash, it's scoria. It's solid material from a volcanic eruption as opposed to lava, which is liquid rock. Anyway, this glacier is partially buried by volcanic material. But that was really interesting because when volcanic material like that comes in contact with water, guess what forms at the boundary between the two? This sulfate salt called jarosite. So it all of a sudden made total sense. There was a glacier there once. The ice might still be there. Eventually, there was a volcanic eruption that covered everything in the region with volcanic ash. Over time, the ash reacted with the ice, created a crust of salt, of sulfate salt at that boundary between the two. And over further time, the surface blanket of volcanic ash got eroded, at least partially, and then exposed the layer of salt that's protecting the ice underneath. So we think that we found a place near the equator of Mars where there might be a large repository of clean water. That's the thing about a glacier. It's not ice buried in dirt in the regolith mixed in. It's meteoric. In other words, it came originally from snow. There is clean ice in a glacier buried under a crust of salt. We figure 1 or 2 meters deep. and in a region that has much more ice actually around that's still completely blanketed by the volcanic material. That's where we were in 2023. We had found a glacier near our proposed landing site, so this was already very exciting for us. But then we asked the crucial question, where does this volcanic material come from? So we started to zoom out, looking for a volcano. Zoomed out further, we couldn't see anything. Zoomed out further, until we were seeing almost all of eastern Noctis Labyrinthus, this maze of canyons, and realized the circular symmetry of these surviving mesas and canyons. The fact that the central point was a high point with sloping outwards on either side, on all sides. All of a sudden, we could see a deeply eroded volcano right there in eastern Noctis Labyrinthus. I mean, in fact, it's not a volcano that's in eastern Noctis Labyrinthus. Eastern Noctis Labyrinthus is a volcano. The whole thing is. This thing turns out to be 9,000 meters tall, so higher than Mount Everest, 9,022 meters tall. 450 kilometers in diameter. So that's the distance between Paris and London, or LA to Vegas. It's not the largest volcano on Mars. It's not the tallest volcano on Mars. But in contrast to all other volcanoes that we know of, which are relatively well preserved, meaning that you can't see their insides, this one is so deeply eroded that not only do you see the outer latest lava layers and eruption layers, but you also see the ancient ones that would have been buried inside the volcano and are now exposed by the erosion. So if you're going to study or ever go to a volcano to explore how it evolved over time, how the chemistry of the rocks changed over time, what features it had, the different eruption styles over time, you would really want to go there. But the thing that's remarkable too is that this ash deposit that was covering the glacier, all of that was very recent. The glacier has to be less than about 10 million years old. The ash layer on top of it has to be even younger, but let's say roughly 10 million years old. Meanwhile, the volcano itself as a whole dates back, we think, to the earliest epoch of Martian history, the Noachian. So the volcano itself, at least at its beginning, dates back to about 3.8, maybe 3.9 billion years old. So now you're talking about a location on Mars that's had a source of warmth. This is a long-living volcano that erupted starting 3.8 billion years ago or so, all the way to the present, on and off, and might still be active today, with ice present in abundance, at least in some parts of it. So you have the ideal place to look for signs of life, past or present, because, with ice you have water, with warmth you have conditions that are conducive to life. You have the salts, which include polyhydrated sulfates, again, which is something we found on Devon Island as well. So you have a convergence of things that are very promising from the standpoint of your search for life on Mars. And all of a sudden, to me, it's hard for me to be objective about this place, but to me it has become the place to be to send humans to Mars.
We're talking about the search for life. I think it was episode 46. Chris McKay did a great job on that discussion.
Yep.
And one of your earlier episodes, we talked a lot about the search for life and what it would look like and how would you know it. And those are both good episodes I commend to the listeners. Now we turn to a related and very fun topic I like. We talk now about two potato-shaped moons of Mars, Phobos and Deimos. As we've mentioned earlier, we both find these things interesting, and I think we have at least 3 blue sky meetings related to Phobos.
Yeah.
Anyway, could you tell us what makes Phobos so intriguing?
Yeah. Phobos and Deimos, the 2 little moons of Mars, were discovered by an American astronomer, Asaph Hall, in 1877. And to this day, we don't know what they are. When you look at Mars, it's a planet. When you see a comet, it's a comet. It's an icy body that's careening back and forth between the inner and outer solar system. When we see an asteroid, we know what that is. They are leftovers from the formation of planets or the debris from, early planetesimals. But when it comes to Phobos and Deimos, many of these hypotheses are still in play. We don't know what they are. So, and then Phobos, of course, is the bigger of the two. It's closer to Mars as well. And on Phobos, you have a glorious view of Mars because Mars subtends 36 degrees in the sky of Phobos, meaning that if you think of your full horizon as being 360 degrees, 36 degrees is 1/10 of your sky. So 1/10 of your sky when you're standing on Phobos is occupied by Mars. So you'd have a spectacular view of Mars. But I don't think Phobos is interesting because of the view of Mars. It's really an intriguing place because it seems to have cracks. It seems to have large craters that are almost the size of the object itself. Phobos is 27 kilometers long, so about the length of, Manhattan Island. And to me, it's particularly exciting, not just because we don't know what it is. Is it the remains of a comet? Is it made of material ejected from Mars following a giant collision, just like our own moon is actually? Is it made of a water-rich asteroid? So in some sense, it's the last surviving or one of the last surviving small bodies that contributed to the formation of the Earth and Mars and Venus as well. So we don't know what Phobos or Deimos are. We should find out. And there's a Japanese mission, a robotic mission that is about to launch. That will go there, collect a sample of Phobos, and bring it back. But the other thing is that Phobos is so close to Mars that it likely has collected a lot of material from Mars.
That's one of my favorite reasons. When this Japanese mission comes back, it will likely be bringing with it the first Mars samples.
Exactly. And it's, not only might there be Mars samples, but they would have been collected on Mars, on Phobos, throughout Martian history, or at least throughout Phobos' history around Mars. And some of this material from early Mars might be better preserved on Phobos than it would even be on Mars, because Mars has an oxidizing environment at the surface. The whole planet is rusted. Phobos, you are talking just about radiation, but aside from that, nothing bad could happen to your sample. So it's really intriguing to see what these missions that would return samples of the soil of Phobos would reveal. But in some sense, Phobos could be this, I describe it as the Library of Alexandria of Mars, where you could have a preserved record that no longer exists elsewhere, but somehow is contained there. From the standpoint of humans going to Phobos and Deimos, I don't think that either of them justifies us going to explore them just because they are so interesting. But in the context of us exploring Mars, I think they are a really welcome stepping stone to making that happen. Now, if you go to Mars with Starship, the idea is that you don't insert yourself into Mars orbit once you get there. You plow straight into the atmosphere of Mars. You do a direct entry. You don't have the fuel to insert yourself into orbit and then deorbit and land on Mars. You have to just go straight in. So a Starship approach doesn't offer a priori any good opportunity to explore the moons of Mars. But in a more classic scenario that would use SLS, for example, you could insert yourself into Mars orbit. And in fact, an early mission to Mars could even forget about landing on Mars altogether and just go to Mars orbit and come back, sort of do the Apollo 8 or the Artemis 2 of Mars exploration, a shakedown of the round trip. And, some people say to me, well, can you imagine the psychological burden of going to Mars all the way and not land on Mars? I'm like, well, if you don't want to go, I'll go. Okay, because I would love to go to Mars and even not land and see Phobos and Deimos and come back. I'd be
In
thrilled.
fact, I'd prefer to go and not land if I'm the first mission.
Okay.
EDL, entry, descent, and landing for the listener, will continue to be an issue. And this is actually my favorite point in favor of Phobos. You're not dealing with the Martian gravity well. So EDL would be much easier.
From there.
To just dock essentially with Phobos instead of trying to land and then escape the gravity well when you want to leave.
Yes.
So much less fuel requirement, much less risk actually early on.
Yeah, and then of course if you're sending cargo and you use aerobraking at Mars, it's actually cheaper to land a certain mass of payload on Phobos than it is even on our own moon. But anyway, the goal would be still to land on Mars eventually. But I see Phobos as being Phobos and Deimos as being really interesting in that context. First of all, you could use them as comms relays. And that's because Deimos is visible in the sky of Mars several hours per day if you are at low latitudes, even relatively high latitude in case of Deimos. And then for Phobos, you see Phobos every 4 hours or so at low latitudes. It shows up, it passes across the sky, and it sinks again. So you could use if these platforms had comms equipment on them, you could use them as a very reliable, stable GPS or basic GPS network to locate yourself. But you could also use them as comms relay to using laser comms, powerful laser comms, with a very stable platform behind them, the moons themselves, to send large amounts of data back and forth between the Earth and Mars. So to me, there's actually there ought to be a strategic race to get to Phobos and Deimos and set up comms and set up shop there, because there's not a lot of room for a lot of human activity there.
No, essentially, they're one flag rocks.
One flag rock, especially with all the dust that you would kick up every time you do something there. There also has been talk about using Phobos and Deimos as places to address the sort of time latency of teleoperating robots on Mars. People lament that the robots on Mars are moving so slowly. If you didn't have the light travel time delay between the Earth and Mars to do that, you could have astronauts on Phobos and Deimos teleoperate the robots much faster. I think that's a flawed argument.
Yeah.
Right?
It did come up at the study that we worked on, and it would be real time, but it's sort of missing the whole point in many ways.
Well, but the other thing is that the bottleneck really in the rover operations is not the inherent mobility of the robot. It's the fact that the science team takes days and hours and days to digest the data that just came back, formulate a new iteration on the science, upload the commands. That process is the real bottleneck. The 20 minute it takes to send the signal is 3 to 20 minutes, 3.5 to 20 minutes is nothing.
It's an engineering problem and a problem for the safety of the rover, not for the science.
Right.
The science bottleneck are the humans.
Exactly. So, even if you were teleoperating a robot from Phobos without the time delay, you would still have, be faced with the analysis of the data that you just collected and, what to make of it, et cetera. So,
yeah. Well, some capability like that might actually shift these archaic work practices.
Yeah.
We see that in human spaceflight. When you're on ISS, every second can be micromanaged.
Yep.
But if you were a human on the surface of Mars, it wouldn't work that way.
Yep.
At least one would hope not.
Yeah. There's an idea that Phil Stuke, who's based in Canada, proposed, which I really like, which is that we could have a decade of, say, tasking JPL to collect samples from Mars, but not just from one location like we're trying to do with Perseverance, but from a large, let's say a dozen locations, in a very uniform way, with ascent stages that are small, just enough to get the samples back to Mars orbit. And they would be stashed on Phobos for the first human crew to Mars, which would not land on Mars, but just do the round trip to Mars orbit, for that first human crew to go collect. That to me is attractive because that human crew would still come back with a treasure trove of Martian samples, which would have been quarantined in a radiation-rich environment in deep space for, anywhere from years to decades before humans bring them back. And so I thought there was quite a bit of merit to that idea of not just counting on pieces of Mars that would be scattered in the regolith that we would bring back, but we would bring back samples that we know where they came from on Mars.
Right. That is an interesting and clever idea. You mentioned Perseverance, and we've been talking about the Japanese mission that may bring back some of Mars from Phobos, and we've been talking about Perseverance collecting Martian samples.
Yep.
I think there are 30 titanium tubes all collected and ready to come to Earth. Tell us about that. First of all, why is it worth the cost? So it'll be, $6 to $10 billion probably, somewhere in that range. And what would we learn if we could get these samples back to Earth? The Mars Sample Return Mission is something we've talked about at NASA for at least 50 years.
Yeah.
40 years at least.
So you're right. Mars Sample Return has been branded as sort of the holy grail of Mars missions. And Perseverance took this huge step of collecting actual samples that one could then bring back to Earth. But to me, the question is that set of samples worth $6 to $10 billion? And if the answer is no, but somehow we're doing other things that would justify that cost, well, what are those other things? And arguments are made that, we'd be launching from Mars, and therefore we would pave the way for humans in that way. I find that argument weak because we're not at all doing anything at the scale of a human mission. We would be obviously, able to have samples that we finally know where they came from, because the Martian meteorites come from unknown places on Mars, whereas these samples, we know exactly where they came from. To me, it's not whether or not we need or would like to have Mars samples. The question is it worth $6 to $10 billion? And the answer from my end is no, not the way the mission is conceived. $6 to $10 billion, that's half of NASA's budget for an entire year when it's, $10 billion. we ought to be able to expect a lot more for that kind of expenditure. And to me, the only way we would justify spending that is if in the process we were really testing a human-landed system, even without humans on board, but a large payload that we would land on Mars, for example, even with a small ascent rocket. If we were testing something that was really big, it might end up costing $20 billion to pull off, but at least it would be in the context of something that really paves the way for humans going. As it stands, as a standalone, just bring those samples back type of thing, with a lot of risk, by the way, in that process, because, you're spending $6 to $10 billion and it might still not work. Because you have to transfer the samples once you're in Mars orbit to a European carrier. The capsule has to re-enter the Earth's atmosphere. I mean, what could go wrong? To me, it's not about the samples anymore in this particular case. If we have $6 to $10 billion to throw at Mars exploration at this point, what should we do with that? And I think that we have to radically retire any outstanding risk that we still have about humans going there. We should, for example, have the ice mapper, which NASA somehow canceled, which was really a good idea. I wasn't even part of that effort, so I'm saying this really, I think, objectively. It's an orbiter of Mars that would really focus on mapping shallow ice. And of course, from the equator all the way to the mid to high latitudes where we might land. It's essentially a water scout in preparation for humans going. Our sense is that our glacier has water ice underneath the salt, but we can't see that water ice. The ice mapper could. And so, to me, that is something that's more important to do than to bring the samples back. Because here's the other thing. Once humans get going on Mars, we will have samples from all over the place and very good quality samples that would have been handpicked, high-graded from different types of settings. We will completely blow away the lessons learned from any small sample that we would bring back at this point. This, to me, is the same problem with sortie missions versus setting up a base. Some of my science colleagues like sortie missions because, well, like we did on Apollo, you go here once and then you go to another place to sample a different location on Mars. And then you go to another place. It's sort of the luxurious sampling buffet tour where you don't worry about setting up an infrastructure. You just go and pick a little bit of everything from different locations on Mars. But that is extremely short-sighted. It satisfies your scientific curiosity in the short term, but it's not a good science exploration strategy. So to me, when it comes to spending something of the ilk of $6 to $10 billion, it really needs to be part of a human exploration strategy to get humans there. And then, of course, Mars science will explode.
Yeah, absolutely. This has been a really fascinating discussion, and thank you so much for visiting and joining us once again on STEM-Talk. Remind me, Pascal, what year did you arrive at Ames?
I arrived at Ames in 1997.
That's when I arrived.
Oh, really?
Yes, I arrived in 97 and departed in late 99.
I see. Yeah. Okay. Yep. Yeah. And I remember your time there. You were. I associate you with big vision and long-term vision and clarity of view. In fact, I was commenting to you this morning when I came visit IHMC. To me, every time I come, I get the sense of visiting the future. It's not the present that is, as impressive as the present is. It's the insight into the future we get when we come visit with you and IHMC. It's unbelievable, and I don't know. It's just super exciting.
Well, thank you. I appreciate the kind words. This adventure, the human adventure, venturing back to the moon and then on to Mars, will be a truly great endeavor. And I hope we as a species and as a nation undertake this bold venture. And we talked about a lot of the challenges, but, one wonders about what's next. You mentioned, and it seems unproductive sometimes to wonder about what's next when we talk about Mars as if we've done it. Some huffy person came up to me about 5 years ago and associated me with NASA, and he was grumpy about NASA. And he asked me why in the heck isn't what he said, had we not sent humans back to Mars.
I see. Okay.
And it's a tough question to answer,
sure.
In a polite way.
Yeah.
But we think about what's next. You mentioned exoplanets. We had Natalie on here on STEM-Talk, I forget which episode, talking about exoplanets. But they're really far away, even the close ones.
Yeah. The analogy I gave is that if the sun were the size of a grapefruit, and you put the sun at the beginning of the Golden Gate Bridge in San Francisco, Pluto is a little pinhead at the distance of the first pillar.
Yeah,
okay, about 300 meters away. Proxima Centauri, the closest star to the sun, is about the size of a large cherry compared to the sun being a grapefruit. It's a smaller star. Proxima Centauri at that scale is in Chicago.
Yeah. It helps people wrap their heads around the scale of this and the distances involved.
There you go.
I don't want to belabor it now because we talked about it a little earlier. It's just, when you talk about exoplanets, we talk about Mars being far.
Yeah.
Whoa. Exoplanets are really far.
Yep.
Well, thank you again. Really appreciate you doing this fascinating interview.
Thank you, Ken. Thank you so much.
STEM-Talk. STEM-Talk.
STEM-Talk. STEM-Talk.
After today's interview, I hope our listeners can easily understand why the Double Secret Selection Committee has invited Pascal to appear on STEM-Talk 3 times. He has such a unique perspective, not only on Mars, but also on our search for extraterrestrial life in the universe. If you haven't had a chance to listen to his first 2 appearances, they are episodes number 17 and number 121. I highly recommend you do so. And since there are plans on the drawing board for manned missions to the Moon and Mars, I am sure the Double Secret Selection Committee will soon be inviting Pascal back for a 4th appearance on STEM-Talk, and that might be a record. This is Ken Ford signing off now until we meet again on STEM-Talk.
Thank you for listening to STEM Talk. We want this podcast to be discovered by others, so please take a minute to go to iTunes to rate the podcast and perhaps even write a review. More information about this and other episodes can be found at our website, stemtalk.us. There, you can also find more information about the guests we interview.